Okay, and there are lots of uses of this. For example, a couple of years ago, I did something applying recognition of people and bicycles, posts that you can look at later, uh, to controlling traffic lights to make bicycle greenways. This is something I presented at GTC, the GPU Technology Conference, which is an annual conference from NVIDIA on basically GPU computing. Um, so, and things again, consumer products, smiling within cameras. Um, Going back thing is something like pose recognition. This is a pose, and, and so to do 2D and 3D pose. Now, where this has is use case. This is Raphael, who's was my partner in Letos company. Here he is driving a car, and we're monitoring in real time his pose. And you can see, we see where his eyes are, where tracking various things are, and we can see how he's looking at his telephone. And this is actually important to actually understand in the automotive case. Okay. Now, here's actually, that's actually my daughter. Here's an application where basically grabbing from the 2D pose and lifting it over to 3D to get a 3D reconstruction of the pose. This is running actually on an embedded platform on a NVIDIA Xavier. Okay. Another classes of algorithms, which are super important right now, are called SLAM, simultaneous localization and mapping. And for this, there are all kinds of different sensors, lots of algorithms. It's the basis for navigation, augmented reality, you name it. This is really important. And I'm actually, I'm in Munich, which is one of the world centers actually in SLAM research, coincidentally. Here is an example of doing SLAM. This is again running on an NVIDIA Xavier embedded board. That Xavier platform is the same kind of chip that's in some of the driving automotive platforms from NVIDIA, their Drive PXs, etc. And what this is it's looking. You can see it's looking at. We're walking around. This is done with a 360-degree camera, and this is walking through a space with the 360-degree camera, doing the algorithm on SLAM, looking at the various key points to build actually a point cloud, a kind of 3D representation of the environment. And if you look on the left, you see this is the sort of path. And if you look at the various points, that's the point cloud that's actually being built. And one of the interesting things here, of course, is something called a loop closure. And that is when you get back to its original location. If you don't have things like an IMU, you need to go into other sort of tricks, and there are actually a number of algorithms in the last couple of years, which is actually doing here. You can see it just the loop closure, which is taking these key points, it's building a kind of index, and then it's finding maps for those key points. Okay, and this is so. Now I mentioned I'm in Munich. And there's lots and lots of SLAM going on here. There's direct sparse photometry and LSD are really main things. What we saw before was warp SLAM. And the difference being is some of the newer approaches or some of the different approaches coming out of TU is taking direct, looking actually at the various pixels, because this is also pretty cool. Instead of using sort of features, remember earlier on I showed that slide about the sort of features where you've designed them and building up various things. Here you're looking actually at the little variations, the illumination of pixels, and you could actually use that to do all kinds of cool stuff. And yeah, and those are coming out of here. A lot of SLAM is really sparse viewpoints, and we need denser point clouds for things like inclusion and other things. Here is a really nice denser point cloud map. This is of Syria. And I'm showing this was supported by the EU here, but it's really good. This is a scan, a 3D scan of this space. Okay. Now, I mentioned that a lot of SLAM is really sparse. Now, if you look here in this space, you'll see these are my points in my point cloud. This is the original image. This is the point cloud of actually doing SLAM. In this case, we're actually COMAP, which is not really SLAM. It's sort of structures for motion, but those are little details here. Now, what's interesting is that surfaces and contours are not just points in the middle of nothing. You can make a kind of assumptions about the real world, about certain kind of smoothness and a certain kinds of continuity. And this was some work that some guys over at Facebook Research and the University of Washington 2018. This is, by the way, my own implementation of their code. They do publish some code, but it doesn't run very well. So I re-implemented it to actually be pretty useful. And so you'll see this area here, this is actually the dense reconstruction. And with this dense reconstruction, if I'm now going to add another image, let's say on top of something I see in the reality, then I can find the sharp edges and know what's behind and what's before to handle occlusion. So this is really, really important for augmented reality systems. Okay. Now, I spoke before about exploiting odometry, looking at pixels and this sort of DSL SLAM, some of the new SLAM. Now, there's something else which was done at MIT a couple of years ago, and I want to show you this because it's really cool and it's a basis of doing some special kind of.
Our world is constantly changing. Many scenes in our everyday lives that are seemingly static, in fact, contain subtle variations and changes that are invisible to us. Imagine you had special glasses that allowed you to see subtle changes that cannot be seen with the naked eye, like small variations in the color of the skin as blood pulsates through it, or the subtle breathing motions of a baby. These changes are hidden in ordinary videos we capture with our cameras and smartphones. Given an input video, for each pixel we analyze the color variation over time and amplify this variation, which gives us a magnified version of the video. In this example, the pulse signal is amplified 100 times. We can also analyze the frequencies of this signal and extract the heart rate. This doesn't require attaching any sensors to the patient, and the accuracy is comparable with hospital-grade monitors. The same algorithm can also reveal imperceptible motions, like the pulsing motions of arteries in the wrist. When a person fixates at a point, the eye may move from subtle head motions or from involuntary eye movements known as microsaccades. Such motions are very hard to notice even in this close-up shot of the eye, but become apparent when amplified 150 times. Invisible motions are also created by mechanical parts, such as the shutter and flipping mirror in a DSLR camera that produce tiny motions when taking pictures. Structures are designed to sway in the wind, but their motion too is often invisible. Amplifying the changes in this video reveals the swaying of the crane's mast and the undulation of its hook.
So we took this, and one of the things in cars is to try to understand the driver. And so what a lot of people use is a company called Ather, which is actually used in a number of cars. Some other people do things like Microsoft and Amazon also have this sort of facial encoding, which is kind of like following Ekman to look at the ways in which the faces are going to understand the sort of driver. But what we found, we can also exploit this video magnification to derive the heart rate variability data to actually get to look at the emotion. We're actually doing this in two ways. We did this with a sensor, but we found we can also do this using this video magnification. So here's an example. On the right. But applied in other kinds of interesting ways for emotion detection. Lots and lots of other hot applications. We've really, barely scratched the surface. There really isn't much time here. I want to have a lot of time for our discussions. But for example, what we do in computer vision is, for example, image enhancements, binarization of document images. For example, see in OCR, one of the standard common algorithms, if any of you have ever used OCR, is like this sort of Unify, and it's looking at the sort of edges and curves of the glyphs of the characters. And for doing this, you need to actually separate the characters from the background because it's only it can only take binary images. They're not dealing with grayscale, so you'd have to do binarization. If you think of old paper, and if you think of crunkled paper, and if you think of all the sort of things that can happen, it's non-trivial. We looked before at image reconstruction super resolution, but it actually goes beyond this, where you can actually do some computer vision algorithms to see things that aren't there because there probably were there, to see behind stuff, to do things like green screen without green screen, deep fakes. I mentioned really earlier along in the talk today, about these adversarial networks. That's what deep fakes are. They're basically two networks running each other to convince each other, one of them producing a fake, one of them trying to guess the fakes until they can't do any more. Captioning, for example, doing object recognition and choosing what's in the various thing to make sort of image captioning. We take all kinds of other sensors. A lot of what we've been doing right now has been, optical cameras, video cameras. But we could use things like UWB radar, which is what we're using, for example, in our Wi-Fi. We could use this to see through walls. wave, which is a little bit shorter wavelength. This is what's often used for collision deterrence in automobiles. Ultrasound for medical imaging. Lots and lots of sensors for image data. Okay. And so here, for example, we have optical character recognition, OCR, scan docs to text. We have license plate readers. Okay. We have vision-based biometrics. This is looking at iris patterns in a photograph to try to actually identify somebody. Very cool story you can read about. Iris things are also used in other stuff. The World Food Program, which is their research unit, which is actually located also in Munich down the road here. They're quite proud of this. This is why I'm also including a screenshot of their web. They use this along with a blockchain to provide food assistance to refugees to identify people because the patterns are pretty unique. There's medical imaging, CRT imaging, image-guided surgery. Robotics, RoboCup. There are competitions, okay? 3D viewing, 3D modeling. Earth observation is increasingly a really hot area in computer vision using AI. So we're slowly reaching the end of the time to go over to the Q&A, but basically we've got one of the things to talk about is the career path and job opportunities. When people talk about AI, it's often in the context of images, and so right now demand is really, really high in augmented reality, and augmented reality is not just gaming. It's this gaming tech or the gamification coming into other kinds of applications within what is here called Industry 4.0 within manufacturing. I showed you that example where I was doing edges in an office. That's also augmented reality, really important in terms of construction coming up. Robotics, automotive, cars are becoming robots, Earth observation, BIM, etc. Okay.